Here's something most people don't know. Magnets aren't actually solid blocks of magnetic force. They're made up of millions of tiny regions called domains. Each domain acts like a microscopic compass needle, pointing in its own direction. Think of it like a massive crowd where every person is facing a different way. When all these tiny magnetic regions point in different directions, they fight against each other instead of working together. In most magnets that companies make today, these domains are scattered randomly throughout the material. Picture a parking lot full of cars facing every possible direction. Some point north, others point south, east, west, and everywhere in between. When these magnetic domains point in different directions, they cancel out much of their potential power. The magnet becomes much weaker than it could be if all the domains were lined up properly. Here's a simple way to understand this problem. Imagine a crowd of people trying to push a car. If everyone pushes in the same direction, the car moves easily. But if half the people push forward while the other half push backward and some push sideways, the car barely moves at all. That's exactly what happens inside most magnets. The domains are pushing against each other instead of working together to create maximum magnetic force. Traditional magnet manufacturing methods create this random domain scatter by accident. When companies melt down rare earth materials and cool them into magnet shapes, the cooling process creates domains that point in random directions. There's no control over how these tiny magnetic regions align themselves. The end result is a magnet that uses only a small fraction of its potential strength. Scientists have understood this domain alignment problem for decades. They knew that if someone could line up more domains in the same direction, the magnet would become dramatically stronger. Think of it like organizing that scattered crowd of people so they all push the car in the same direction. The force would multiply instantly. But knowing about the problem and solving it are completely different challenges. Previous attempts to control domain alignment during production have failed for several reasons. Some methods worked in laboratory settings but couldn't be scaled up to mass production. Others were so expensive that the resulting magnets would cost too much for practical use. Some techniques could align domains in small samples, but couldn't maintain that alignment in larger magnets that companies actually need. The manufacturing challenge comes down to controlling what happens at the microscopic level during production. Companies need to influence millions of tiny domains simultaneously while the magnet material is being formed. Traditional methods like heating, cooling, and applying magnetic fields during production only create partial alignment at best. Most domains still end up pointing in random directions. What makes this particularly frustrating is that the potential for stronger magnets has always existed.